Again, everyone, Nate here. I want to talk about the all-wheel drive systems today on the SVX. There are 3 different drive types that you can get. The all-wheel drive system found on US models, which at the time was the same as came out on the 88.5 XT6, full-time all-wheel drive using multi-plate clutch. Sometimes we call it ACT4. Whatever name you want to use, this is the traditional Subaru all-wheel drive that's still in use today on these CVTs. Then of course, 94, 95, we have the 2-wheel drive, and then we have VTD, which was introduced on the SVX and in Japan and several other regions, and didn't make an appearance in the US, unfortunately, for several reasons. But anyway, so let's talk about front-wheel drive first, because it's the easiest. So even though the SVX was never intended to be front-wheel drive, you know, in 94, they're like, well, we can make one front-wheel drive. It's not really that hard. Keeping in mind the transmission itself is pretty much the same as every other Subaru model. The only difference is that the clutches are weaker, you know, as the engine is smaller. But, you know, the design of it is the same. So they said, well, let's just make an SVX transmission without the all-wheel drive stuff. Let's make it just like we make Legacy and Preza 2-wheel drive transmissions, and that's what we have. So basically, you have all of your transmission stuff here where I've written the word trans right here. So basically that's all the gears, all the transmission stuff's going on is happening right here. And then that comes over here to what's called the reduction drive gear at the very back of the transmission. This behind that is the extension housing. That reduction drive gear meshes with the reduction driven gear, and then splined to that reduction driven gear is the pinion shaft for the front differential. Pinion shaft, of course, drives the ring gear. Differential action, we got front wheel drive. You can see this is all gears. They're directly driven. Front wheel drive, very easy to understand. So for the traditional clutch type all-wheel drive, what we're gonna do is the back of the reduction gear here, the reduction drive gear, we're gonna weld a clutch hub. What that's gonna allow us to do is have that interact with some clutch discs, some friction discs, you know, so it's splined to these, well, I've shown them in brown here. And then in between friction discs, of course, because we have a clutch, there's friction disc and then steel plate, friction disc and steel plate, where the friction discs are attached to one component and the steel plates are attached to another, and they're rotating at different speeds. And then, of course, what a clutch does is it squeezes those together, and then we get speed equalized. Now on these cars, the steel plates are splined to the output shaft for the propeller shaft for the rear differential. So we have our, you know, our rear differential and rear wheels there. So basically what we have here is a device, I call it a power takeoff device, because remember, we still have this front wheel drive setup. So we're still directly geared to the front wheels. We cannot change this relationship between this direct gear to the front wheels, okay? However, by manipulating this special clutch, we can change how much torque is applied to the propeller shaft as a percentage of the torque available here. So it's important to note that because this is directly geared, I can never turn the output faster than this gear here. Okay, so I can never turn the rear wheels faster than I can turn the front wheels. And similarly, I can never get more torque at the rear wheels than I can at the front wheels. So what we're gonna do, the way we're gonna do this is we're going to change the pressure that's squeezing those discs together, and that's going to change the amount, as I said, of torque going to the propeller shaft for the rear wheels, up to a theoretical 50%. Now, we're going to do that using a duty solenoid, and of course a duty cycle, you have on-off signal, which translates to a percentage of time that the solenoid is either on or off, depending on whether you got a normally open or normally closed solenoid. But basically just saying that's how that works. So you can kind of see that I'm going to chop that fluid, and that's going to reduce pressure going through it. So we have mainline pressure coming into the back side of duty solenoid C. Out of the valve body, there's a special little pipe that heads back there. And then we've got our duty solenoid C, a duty cycle that's going to change the applied pressure to the clutch. Now, as this applied pressure changes, torque changes to the rear into, like I said, a theoretical maximum where we theoretically have this clutch fully engaged and we've got full lock. We've got this clutch pack is completely locked. The rear output speed matches the front speed. Now, in this system, we can't really do that for several reasons as far as the actual fluid system and how it works, but we wouldn't want to do that because if we tried to do that and something happened where these two speeds became different, it would destroy this clutch. It's already a bit of witchcraft that Subaru is able to use a clutch that is able to actually slip, because in most clutches, what you're going to do is you're going to start your clutch engagement and the speed's going to synchronize using the fluid, and then the clutch is going to stick together and the whole clutch rotates as one unit or stops. But they use a special clutch plate here so that it's designed to slip partially a little bit. That's really unusual, and it's pretty trick stuff. If we allow a clutch to slip a little bit in transmission, generally, like for our shifting clutches, that's what we call a bad transmission. That's when our transmission's burnt up. But anyway, we're gonna do that here. So the really cool thing about this clutch, what makes it special, is that it's got some intelligence to it. So we have this duty signal that we can vary however we want to change the supply pressure on this clutch. Well, how are we going to do that? We're going to look at several different factors. Of course, speed sensor 1 back here on the rear output, speed sensor 2 up here on the front differential. I'm going to look at throttle position, I'm going to look at gear position, and a couple of different things. And what I'm actually going to do, and this is the really cool part about this that differentiates it, especially at that time, is it's going to work on a mathematical principle called predictive modeling. So instead of just changing the all-wheel drive torque split based on the wheels slipping like Honda does and a lot of other manufacturers do, so it's basically two-wheel drive until the wheels slip and then it comes on, that's kind of stupid. Subaru obviously agrees with me. There are still to this day some systems that work like that. That's total nonsense. I don't know why you would want to do that. But this does not work that way. Keep in mind, in 1988, 87, this is really trick stuff. We've got a pretty, at this time, the TCU we have running this transmission is more powerful computationally than a lot of manufacturers are using for their engines. And at this time, General Motors, they're not even using computers yet. So we've got our computer, and it's got a lookup table. So the computer is going to say, if throttle position is this, and gear position is this, and this, and this, and this, then I'm going to put out a certain duty cycle to the transfer clutch. And then once that duty cycle manipulates the solenoid, that'll become an apply pressure and a torque transmitted here. So we're going to use predictive modeling to predict when we would want more torque here to prevent wheel spin. So we really want to get ahead of the game here. Okay, so we don't want to react to wheel spin, we want to prevent it. neat, right? This is actually a really cool thing that they did way back in the day. It's still pretty cool today, to be honest with you. So, you know, you look at things like, you know, as my throttle pressure is higher, more chance that the wheels are going to slip. So as the throttle pressure goes up, you know, as the TPS signal increases, more apply pressure. If you're in first gear, either, you know, manually in first gear, or the transmission just so happens to be in first gear, more chance of a wheel slip, so we're going to have more apply pressure here. Manual second is also very aggressive. However, fourth gear with the cruise control on, I don't want to say that this is off, but we're super close to off. We've basically just got enough fluid going through here to lubricate it, and a little bit of static pressure on the clutch. But, you know, straight road, 70 miles an hour, you're pretty much completely front wheel drive. Now, the opposite is true. If you're in a car and the TPS is adjusted correctly, your line pressure is good, and that's a huge if. That, you know, that's for later. But everything was working as it was designed. If I'm in first gear and I floor the car, I've got a lot of pressure here. So I'm gonna be pretty dang close to a 50-50 torque split. I say that pretty dang close. I shouldn't oversell it. You know, I don't know the exact values because it's not really possible to calculate them, but I would estimate we're at 30, 35%, if not 40% of the torque available to the front wheels is also available to the rear wheels. So keeping in mind, like I said, we cannot have this clutch at full apply, because then if we turn the car will either bind or it'll destroy the clutch. So we cannot lock this thing up completely. It's one of the major limitations of this system. But what does that really do? Well, you know, obviously when the car is not moving, we're not concerned about the torque split, because it's academic. It doesn't really matter until there's actually torque being transmitted to the wheels. But as soon as the car starts rolling, you know, as soon as you let off the brake, we basically got pretty much all the torque we can get out of the engine is going to be plenty for the wheels. However, we're still going to be front wheel bias, because remember, it's not possible to have a rear bias. So that's how that works. And then I use the extreme of cruising down the road, and then the other extreme is, you know, full throttle acceleration in first gear. One of the things that really I always thought was really kind of silly about this system is that, and people have argued about this in the SVX world and in the Subaru world in general for years upon years, probably since 1987. What's the torque split? Okay, what is the torque split here? It's somewhere between 0% to the rear and the theoretical maximum of 50% to the rear. If you try to give that a number, you're underselling this system, okay? It's way more sophisticated than that. What is, you know, people will say, well, my torque split's, you know, 20% to the rear. You know, it's 80-20 is the torque split on SVX. And I'm like, sure, sometimes. You know, depending on what the computer calculates, there is a time when that's true. And then another guy says, well, you know, mine's, you know, 60-40. And I'm like, probably right. Absolutely. I'm sure there's a time, you know, in this dynamic system that you're right. There is 60-40. The only thing I will not ever agree with is, you know, it can never even be 51% back here. That's theoretically impossible, let alone actually operationally. So whenever someone asks what the torque split is, you say the torque split is infinitely variable to the rear. It's whatever it needs to be. Okay, so we've covered how this operates during normal operation. Of course, I've not spoken about whenever the wheels slip. So as I said, we have a wheel speed sensor back here checking the speed off the propeller shaft, and a wheel speed sensor up here checking the speed of the ring gear on the front differential. Now, of course, you know, in turning there are minor differences, but just to make it simple, let's think about the car going straight down the road. So we always want those two sensors to be equal. If they're different, that means that we have, you know, one or more of our wheels traveling, you know, rotating faster than the others. So what does the TCU do? The TCU says, oh, whoa, whoa. So it basically goes to max apply. It doesn't do it immediately, and I will tell you the reason why it doesn't do it immediately. And I found this out through experimentation, because if you make it do it immediately, the car becomes very poorly behaved in poor traction weather. You'll be driving along and you think everything's just fine, and then all of a sudden the rear end of the car just slides all over the place. So, but it very quickly ramps up that apply pressure, so that, you know, it's going to equalize the two wheel speed sensors, and then once they're equalized, it goes back to its regular intelligent predictive modeling. Now, when we think about this system, it's beautifully simple. It's awesome. I mean, obviously, since they've been using it for as long as they have, it's so simple. It works really well. It's proved to be pretty reliable. Me personally, I wish that we had the option, especially in the SVX, of doing the exact opposite. So instead of using the power takeoff for the rear, I wish that we had done a power takeoff for the front. And that way we would have a strict rear wheel drive car that was sapping power to the front wheels. Subaru didn't do that. You know, again, it wouldn't have exactly been rocket science to just change where the transfer hub was welded. Because all you have to do is instead of welding to the reduction drive gear, you know, just weld it over here, and then have the pinion shaft here driven by your steel plates. Not hard, right? And then this could be a straight shot to the rear, just like a rear-wheel drive transmission. You know, I've wondered why they didn't do that. Again, it's not hard to wonder why, because that's a whole redesign. And remember, other than the SVX, they're not trying to build a performance car. They want a car that's going to drive well in low traction situations. Generally, that is a more front bias system, especially, you know, we're many years at this point before mainstream traction control, stability control, and all that. So, cool, system works really well. What are the problems with this system? Duty solenoid C failures, extremely common, especially as the cars age, the fluid gets dirty. It's a pretty easy replacement. The symptoms of that are low apply. Lots of times the car will just basically be in front wheel drive because the duty solenoid C is no longer really operating. So it's pretty much blocking, or, you know, it's either blocking it or holding it wide open. So you either have binding or you'll have no apply. Now the binding is kind of the worst of the two scenarios, because as you start to have binding, what generally happens on these is people continue to drive it that way, and these welds right here where the clutch hub is welded to the reduction drive gear are not really all that strong. So I've seen quite a few of them shear that off, and then you know, sometimes you won't even know that, but usually it'll make a pretty interesting noise whenever turning, and then of course once this is sheared off, obviously none of this will work. Regardless of what the clutch is trying to do, it's no longer has a connection to the power. The early SVXs, there is a problem with some of the Teflon sealing rings and the case that causes the fluid, the applied fluid in the transfer clutch to bleed off. You know, it escapes where it shouldn't escape, which causes low apply. Then of course, our main problem with this transmission in general is low line pressure. And of course, remember, we're varying the applied pressure to this clutch based off main line pressure. So if main line pressure is already low, the calculation that we're gonna make is gonna be starting out that low as well. It's pretty common for an SVX transmission that's in bad shape to really not have a lot of apply back here. It's kind of obvious if you're familiar with SVXs. You can jump in and it'll have a little bit more torque steer than you're used to on this system, and you can just kind of tell that it's not working as well as it should. But if it's your SVX and you drive it every day, it generally happens pretty gradually, so you don't notice it. But that is one of the things that I look for when I test drive an SVX. I'll get on it pretty hard in a corner and see how much torque steer I have. Now, of course, we have all SVXs have a viscous coupling in the rear differential, open front differential. That is what it is. There have been some modifications to the front differential. I think one of the guys was using a kit out of a Porsche or something. I wanted to do it on mine, but I never got around to it. Much like many things on that car. So anyway, so we know how that works. Pretty cool, right? Still in use today. Worked just as well on the 88 XT6 as it does on the 2021 Crosstrip. So VTD. What are we going to do with VTD? I want you to think about this system and everything I said about the clutch, the predicted modeling, and all that. That's going to carry forward into VTD. The main difference that we're going to have in VTD is between the reduction drive gear and the clutch hub. So right in here, we're going to have a planetary gear set, right? So we're going to have our, our planetary gears in here. And then of course, this is actually kind of what it looks like. And then, instead of having a clutch hub welded to the back of the drive gear, you've got a ring gear that engages with these planetaries. And of course, these gears are splined here. And then, I believe that's right. Someone correct me if I'm wrong. And then I think the sun gear is splined to the rear. Anyway, this is not important, but so you've got a planetary gear set here, and that planetary gear set is an actual differential. Remember, the regular system has no center differential. The clutch does the whole thing. It's the whole shebang. This one, we've got a actual set of gears, and due to the mechanical teeth and interaction of the gears, we have a mechanical torque split of 36 to the front and 64 to the rear. That's calculated based off the number of teeth on the gear set. Now that is unique to the SVX. Every other VTD has a different torque split, and it's more front bias. So now the main thing that we've gained here is, due to the nature of the differential, we can turn the front, the pinion shaft and the reduction driven gear and the propeller shaft at completely different speeds. So in that way, I can actually send more than 50% of the torque up here, and I can send more than 50% of the torque back here. And of course, due to the nature of the torque split, if we don't have any kind of limited slip device on this, what would happen is your torque split is 36/64 until one of the wheels starts slipping. And as soon as one of the wheels starts slipping, whichever wheel is slipping, then it's 100% to whatever wheel's slipping. Now, of course, we don't want to do that. So we're going to use this same clutch. Now it's much smaller. The clutch capacity is smaller, but it still has a duty solenoid. The duty solenoid looks pretty much identical. and it's still got a clutch back here. But the main difference here is that this clutch is no longer used to vary the torque between the front and rear wheels. The purpose of this clutch now is to suppress the differential action of my planetary gear set as a limited slip device. What does that mean? So like I said, the nature of a differential is it's gonna follow the path of least resistance, right? So if I just let it do whatever it wants, as soon as the wheel slips, why do we even have all-wheel drive in the first place? Because we're just gonna turn whatever wheel is spinning. So we're gonna use the clutch. Now, the clutch is gonna force the differential to be static. And what I mean by that is the whole thing is gonna rotate as a unit instead of it performing differential action. We're still gonna use this predictive modeling though, because we just wanna, drag on the clutch a little bit so that there's resistance to it. So that there's a resistance of the clutch differential action, just in case it were to slip. And then of course, same thing as with the other system. If there is a wheel speed difference, then we're gonna go to full apply here. And what that's gonna do is it's gonna stop that differential action. Okay, so it's gonna say, no, you no longer get to move the stuff around according to your natural tendencies from the gears. I'm gonna stop you and you're gonna rotate as a complete unit. So that's the variable torque, right? And of course they use all these mathematical tricks that are a little bit confusing because the torque distributed only really means anything if that torque connects with the road. So, if you talk about a wheel that's spinning, say on, it's up in the air, how much torque is going to that wheel? Well, it depends on how you look at it. It's either some arbitrary percentage or zero, because no torque is being transmitted as actual motive force because that wheel's not moving anything. So we have our 36-64 ratio here. So when this clutch is at full apply, technically it's gonna just lock in that unit to 36-64. Then again, depending on how you wanna look at it, it's also gonna cause this whole thing to rotate as a unit. So you could also say that on full apply, we have 50-50 distribution. They like to say that the VTD system can be 100% front or 100% rear. Now, while on paper that's technically true, we wouldn't want to do that because you could damage the planetary. It's very tough when operating correctly, but it wouldn't stand. Say you're running the front wheels at 40 miles an hour, and then all of a sudden the rear wheels catch. You could damage that. Plus, it's just not designed to do that. So realistically, we don't ever have that kind of torque split. We have 64 here and 36 here, and we're gonna move in that area somewhere between 36-64 and 50-50. Okay, and that it sounds like it's a smaller area of variation than the MPT clutch, but it's really not. And the effectiveness of the clutch, keeping in mind that it no longer bears the burden of trying to actually run the whole torque split mechanism, is so much lower. This system is faster, it's tougher, and it works better in every imaginable way except for fuel efficiency. Because as you can see, these gears mechanically link all this stuff. So when I'm cruising down the road, there's not really any way for me to manipulate this torque split and take off the frictional losses of either axle. It's also not possible to put this in two-wheel drive. Now, technically, you could block two of the wheels, disable the clutch, and then it would run only two of the wheels, but that wouldn't be safe to do on a dyno, and you'd probably damage it. For that reason, you can't use a VTD car on a two-wheel dyno. And the concern at the time in the 90s with Subaru was that it was quite a hurdle to get an exemption for a full-time all-wheel drive car at that time. There were some that had it, but not really very many. Even Toyota, on theirs, they had a special like bolt you could remove underneath the car and rotate a cam, and so a lot of people had figured out these ways to put it in two-wheel drive. That's one of the reasons VTD did not come to the United States until 2001 in the Outback VDC. So anyway, VTD is way better. If you've driven an SVX with VTD in it, it more matches the balance of the chassis, and you can just immediately tell that this is how the car is supposed to drive. It changes the whole character of the car. It makes it drive way better. 10 out of 10 recommend. The 5-speed cars, the Legacy GTs and stuff with the 5E in this system are nice driving cars as well. However, they don't have the rear bias that this one did. These parts, all of these parts, are completely unique to the SVX. The imports for us in the United States, there's Legacies and Imprezas overseas use VTD in the 90s as well. None of them have this same bias. And the clutch is different as well. So all these parts are SVX only. For that reason, if you have one of these VTD SVX transmissions and you junk it, there's a special place in hell for you. If you have another transmission that you want to try to run in here from a Legacy or an Impreza, I believe it may work. I've heard stories about having binding issues with those, but the only person that I really heard from a story about that, he didn't know what he was doing. So I don't know whether or not that could be resolved. All right, so then let's talk about the manual really quickly. How do those work? The manual doesn't have any of this fancy stuff. The manual just has a viscous coupling. What's a viscous coupling? So we have a clutch, it's not a clutch pack, but we're gonna call it a clutch pack. And again, we have alternating discs that are, rotating at a different speed. And I'm tired of drawing, so there's more than that, but in our example, there's only gonna be that many. And then in between each of these is a special fluid, a special viscous fluid that's, sticky and all that. And so what basically happens is that fluid expands whenever it gets warm. So when these two discs are rotating as a unit and no slipping occurs, everything's golden. The fluid's just kind of bouncing around there, not doing anything. Now the second that, the drive plates and the driven plates run at a different speed, that fluid gets hot and starts to expand. And so that causes a equalization of the torque. Now, they don't work that well. It does work as an LSD, but it's got an apply curve, that's going to go up like this. So if you've only got a small wheel speed difference, there's not a whole lot of transfer between here. These also tend to wear. I'm just not really generally a fan of viscous LSDs. They've been out of favor for many years now in favor of Torsen. But this is what we use in the rear differential of SVX, and this is what all of the Subaru manuals use in the center differential except for the STI. In the US, there may be others in other countries that use that. But also, when we have a manual, we have a conventional style differential, just like the one we use for the front and the rear wheels. So that one is not like a planetary. So it's just basically a flow through device. So it's gonna be 50-50 torque split. Which works. You could say in a way that's better than the MPT system that is always gonna be front biased. I personally don't think so. I never really liked the way that those drove. That is definitely the weak link in the Subaru arsenal of all-wheel drive systems. As I famously forgot a while ago, they actually do a pretty trick thing here where this is sleeved. so that it will allow the front wheels to rotate at different speed than the rear wheels. It works if that's your cup of tea. Both of these systems are way better functionally. That's one of the main reasons why I'm just not a fan of manual transmission SVXs, because it takes the car down like several notches in technical sophistication. And I'm not even talking about the manual transmission part, I'm talking about the all-wheel drive system. VTD, of course, we have very limited experience with this because there are so few of them here in the United States, and you know, with it being unique to the SVX, I haven't really heard of any problems with it. I'm sure after all this time, somebody somewhere has had a clutch go bad or blown up the planetary or something, but it's way more reliable than the MPT system is gonna be. What would be the symptom of a bad duty solenoid C on VTD? The same thing, depending on how it was failing. You would either have binding, because when you turned it would lock that differential together, or you would have no limited slip effect, which you probably would only notice if you slipped a wheel and then all of a sudden all the torque went to the slipping wheel. I would like to mention that the main advance in these systems came, I believe it wasn't till the 5-speed, but I could be wrong, is that instead of monitoring wheel speed here and wheel speed at the front differential, they started using the ABS wheel speed sensors, which made the system work a lot better. Not that it already didn't. On either the VTD or the MPT system, if you put an SVX up in the air and you put it in gear and the wheels are rolling, even if you're don't have any gas on it, it's just idling, and you go up there and try to slow down one of the wheels, before you can get that wheel stopped, it'll jerk it out of your hand. I don't know the exact number, but it's like maybe half a rotation of the wheel before the system is going to react. That's why if you look at this system when it's operating correctly, you can, if you get a wheel that slips just a little bit, assuming it's not on something like glare ice, but say it was just wet, you may see that wheel like turn one turn or a half a turn ahead of the others until it grabs it and it goes. And keep in mind also that unless we're in a super low traction situation, by the time the power is moved over to one of the other wheels, by the time that process has happened, the car has accelerated to a pretty fast speed. So the potential to slip the wheel is no longer there. That's about it for the all-wheel drive systems. Like I said, main takeaways on this: the VTD is dramatically superior. The SVX should have always been VTD. It's very tragic that it wasn't, but it is what it is. Probably the best conversion that you can do to an SVX, if you want an SVX to be an SVX, is the VTD conversion. It's not hard. You either put the VTD transmission in a US car and then put the VTD TCU in the car and you're good to go. Of course, you have to match the rear differential, or you can build a VTD section onto any transmission you want. That one thing I forgot to mention, and I apologize: front wheel drive, 3.70 ratio here. VTD car, 3.70 ratio here, 3.70 ratio here. The US traditional MPT setup, 3.54 here, 3.54 here. I did make sure to say that they were the same in front and rear, because for a couple of years, very strangely, they made, I believe it was a WRX that did actually have different ratios, front and rear differentials. All right, guys, well, that is the all-wheel drive basics on the SVX and all of Phase 1 480 transmissions from 87.5 to 98, early 98.